Hello, everyone. Let me walk you through this week's lab. We're going to be investigating a spring pendulum. So here I have this spring with a mass in the end. We'll pull it down and we'll watch the oscillation of this spring pendulum, and we'll time how long it takes for one full oscillation or the period. And then we're going to change the mass out and then record the period in that new situation. That will give us a big table of data here of different masses along with their corresponding periods that we measured. Our goal here is to get the spring constant of our spring. Well, we want to do this through a plot. So how are we going to do this? Well, just like normal, we're going to start with a physics equation. T equals 2 pi the square root of m over k, where t here is the period of the pendulum, m is our mass, and k is the spring constant. Well, we want to be able to plot this, but in our y equals mx plus b equation, there's no square root. And that's okay. We just need to rearrange this term a little bit. And to get rid of the square root, we're going to square both sides. So that gives us t squared equals 4 pi squared m over k. Remember, m over k used to be in the square root, but now it's not because we squared both sides. I'm going to rearrange this a little bit so it's a little more easy to see which one's y and which one's x in our linearization process. So I'm going to divide k over to this 4 pi squared term. I'm going to add a 0 on the end. So I just moved things around a little bit. Hopefully you can see where the y and the x are. So here we have in the y position we have t squared. And in the x position, we have the mass m. Now, we got to be careful here because there's an m here in mass in our physics, and there's m here for the slope in the y equals mx plus b equation. So try to pay attention here which m you're looking at because it can be tricky. So speaking of, this m in the slope position is in the 4 pi squared over k in our physics equation. So we can take our slope, set it equal to this to eventually solve for k, and our expected value for our y-intercept is 0. Now, if you notice, we don't have t-squared data. All we have is period data. This is our measured data. And that's okay. We just need to make a new table of data where we square each of those period terms because this is what we're plotting. We're not plotting mass versus period. We're plotting mass versus period squared. And then when we do that, our slope value is 4 pi squared over k, and our y-intercept value is 0. All right, so we're going to take that data and we're going to plug it right into Desmos here. So here I have x and y. And so remember, x is what we're plotting on for our mass. So this is all of our mass data here that we plugged in. And then in the y-axis is t squared. So remember, not t, but t squared. We're going to plug all those in here. And Desmos is going to do a best fit line and output a slope and an intercept for us. So here our slope value is 6.41 and our y-intercept is 0.102. Our goal is to get that spring constant k, and we can use this linearization that we've done to get there. So if I know slope value, which I have here, I could just set that equal to 4 pi squared over k. And so remember, this is m for slope, not m for mass. So all I have to do here is just solve for k because I know everything else. So I can multiply k to both sides and divide m to both sides. And that gives us k equals 4 pi squared over m. We can plug in our values, and we arrive at 6.17 newtons per meter. Our y-intercept here is 0.102. The expected value is 0, and it's okay that we don't get that value because there's uncertainty in our experiment. So in the way that we're timing our data, there's going to be some variation in what values you get. And so it's fine that we're not getting that 0 value. In fact, it's expected. All right, so for this lab, we got 3 steps. The first step is going to be we're going to be acquiring this data, and I'll walk you through the simulation here in a minute. And then we're going to be plotting the data. Now, when we acquire the data, we're going to get mass and period data, but we're not plotting mass versus period. We've got to do period squared. So be sure that you square those values when you plug it into Desmos. And then we can, from our plot of our data, we can get the spring constant from the slope. And the third step, you're going to answer some questions about this in the lab assignment module. All right, let me walk you through the simulation. So when you go to the link, you're going to write here. We're going to click on the far right. This is lab. And there's a couple of things we're going to change. First, we're going to take the spring strength and we're going to drag it all the way to the left. Okay, this is very important. Use the smallest value for spring strength. Then we're going to take this orange mass, the one with the number on it. I'm going to hit stop so it doesn't keep going up and down. And I'm going to take this timer and we're going to drag it over here. This is what we're going to use to time the period of the oscillation. And I'm going to start with 50 grams for our oscillation because that's the first data point that we're interested in. And so we're going to pull it down and we're going to let it oscillate. Now we're going to time 10 periods just to kind of reduce the uncertainty of how accurate we click start and stop on the timer. because by doing it for 10 periods, we're only clicking start and stop twice for 10 oscillations. All right, so I'm going to start the timer when it gets to the very bottom, and I'm going to start by saying 0 so that I make sure I count full to 10. Here we go. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, so I arrive at 8.14 seconds for 10 oscillations. So for one oscillation, I divide that by 10 to get 0.814 is the time of one oscillation. So when we go over here to Desmos, you'll notice a couple of things. First of all, this says 50 grams, but we need to convert that to kilograms. So to go to kilograms, we divide by 1,000, and that arrives at a mass of, this is my previous number, at a mass of 0.05 kilograms. So this is 50 grams, 70 grams, 90 grams, 110 grams, and so on. Well, now in the y-axis, we're not plotting the period. So here our period was 0.814, but we got to square that. So I'm going to get my calculator out, and I'm going to do 0.814 squared, and I get 0.66 is my time. So for period squared, I'm going to put 0.66 here. And it gives us our first data point. So the next data point is with 70 grams. So 0.07 is 70 grams. So I'm going to go over here. I'm going to drag this to 70. Here we are. And then I'm going to do the same thing. Clear my timer. And then we're going to time 10 oscillations here. So we go 0, 1, and so on. Once you get to 10, you'll divide that number by 10. You'll square it. And that's the number you'll put here for this part of the data table. And do that for all of these. Once you've done all that, you can. This is going to give you your slope and your y-intercept value, and that's what you'll use to answer the questions and to be able to determine the spring constant of this unknown spring here. All right, I hope this helps. Let's get to it.